to everybody. Welcome back to my channel. So today I just want us to go through some of the mathematical questions so that it will prepare you as you also prepare towards your semester examination. So I want us to look at some of the past questions, and we will look at the number 1 and the question 3. So as you prepare for your internal assessment, we've been pre-informed that mathematical induction will not be part of the income and internal assessment tomorrow. So we'll start from question 1b, then answer question 3. The whole of question 3 will answer inshallah. Then question 1a we'll find another time and answer it. Without wasting much time, I think we can start working on the answers to the questions. So the B part of question 1 reads: find a counter example to disprove each of the following statements. For every positive integer n squared plus n plus 1 is always a prime. So we are going to find a counter example such that there will exist an integer. So there will exist an integer, let's say x, which is what an integer, and it is not what divisible, and it is not a prime number, such that x is not a prime number. I want to cancel it. Is okay. There exists an integer x such that x square plus x plus 1 is not a prime. So this is what we are basically going to show with counter examples. So you are my friend. Let's continue. Okay, so let's this be a guide. So for every n in Z, they are saying that n squared plus n plus 1 is prime. That means a prime number, any number that has only two factors, 1 and itself. So if we are going to list non-prime numbers, I think 0 is not a prime number, 1 is not a prime number, 4 is not a prime number, 6 is not a prime number, and so on. But 2 is a prime number, 3 is a prime number, 5 is a prime number, 7 is a prime number, 11 is a prime number, and so on, because it has only two factors, 1 and itself. I'm cancelling it. So with this in mind, let's find a counter example. Integers consist of both what? Negatives. So negative whole and positive whole numbers. So 0, 1, going. Okay. So these are integers. Negative 1 up to infinity, 1, 2, 3 up to infinity. So this one too is up to infinity. So negative 1, 0, 1, 2, 3. So if we test negative 1, we have negative 1 square plus negative 1 plus 1. So negative 1 square plus negative 1 plus 1 should be what? The claim is that, the statement is that this is what? True. Sorry, this is a prime number, so we are going to disprove it. So negative 1 square is 1 plus negative 1 is 1, negative 1 plus 1. 1 minus 1 is 0, 0 plus 1 is 1, but 1 is not a prime number, so there exists. After this, even you can use 0. 0 square plus 0 plus 1 is not a prime number, so that means there exists an integer. So we are going to conclude that there exists, you can use this symbol, there exists an integer, there exists a negative 1 in integers such that negative 1 square plus negative 1 plus 1, which is equal to 1, is not a prime. That is your conclusion, and that is the solution to what? The first question. So let's look at the B part. So let's look at okay, this is B, right? So let's look at, okay, it's BI, so we are done with the I part. We are going to look at the II. If n is an integer and n squared is divisible by 4, then n is divisible by 4. This one too, we can easily find a counterexample to the question. Easily find a counterexample to this question. Okay, so they are saying that if n is an integer and n squared is divisible by 4, then n is divisible by 4. We know that negative 2 is an integer, and negative 2 square, which is equal to 4, is divisible by 4, but negative 2 is not what? Divisible by 4, doesn't divide 4. That means that negative 2 doesn't satisfy this statement. So there exists negative 2 in integers such that negative 2 square is divisible by 4 and negative 2 is not divisible by 4. Or there exists 2, we can also use 2 in integers such that 2 square divides 4 but 2 doesn't divide 4. Okay, and that is the solution to the question 1b. So let's look at the final part, and this needs some time to analyze and solve. Okay, but it's not a big deal. So we are going to look at the question 3, A, B, C all together. So be with me as we dive into the solution of question 3. So the question is that A is given as this and B is that. So we are going to find A times B. So we are going to find the ordered pairs for this. So we are going to take the members of A and distribute it over what? The members of B. So if I take 1, I'm distributing 1 to both A and B. That is the members of B. So they are ordered pairs. So we have 1 comma A, 1 comma B, then we take 2 again. We will take 2 comma A, 2 comma B, then we take 3 comma A, 3 comma B. You are done. So this is for the A part of question 3. Okay, so the next one is B. Let I is equal to this, and for each I in I, let AI be that. Okay, so the first question is that we should find AI for each I in I, for each small I in capital I. Okay, so we are going to find so the I, we are going to find A1, A2 and A3. So we have 3 small i's. So our AI is equal to this. So A1 will be equal to, so currently our I is 1. So A1, in place of the I we are putting 1, because I is this 1, 2, 3, and this small I is a member of the big I. So if I is equal to 1, it's just like we are saying that I is equal to 1. It means that A1, so A1 will now be what? So we substitute 1 here. Wherever we see I, we are putting 1. So I, so we'll put 1. I plus 1, 1 plus 1, which is 2. I plus 2, 1 plus 2, which is 3. I plus 3, which is 1 plus 3, which is 4. And this is it. Then A2 is equal to the same thing: 2, 3, 4, 5. A3 is the same thing: 3, 4, 5, 6. And this is for the I part of question 3. Is it B? Question 3B. Then we are going to look at the II. We're going to look at the II. So we are going to find the intersection of I in capital I, AI. So that means we are going to find this is called to what? A1 intersection A2 intersection A3, which is called to what is common between the 3 sets. So we have 3 and 4 in all the 3 sets. So it is 3 and 4. And the I, we are going to find the union I in capital I, AI. That means we are going to find the union A1 union A2 union A3, which is equal to, so 1, 2, 3, 4, 5, 6. This is the union. 1, 2, 3 and 4 are repeating, so we already have 2, so we don't need these 2. So we pick 1, 2, and 2. We already have 2. Then 3, 4, 1, 2, 3, 4. We have it. So we don't need 2, 3, 4 here. We only need 5. We don't need 3, 4, 5. We only need 6. So our union is 1, 2, 3, 4, 5, 6. Okay, and that is it for the question 3B. I. My board is dirty. Let me clean my board. Okay, so the other question, since it's a different question from this. So maybe we'll pause the tutorial and continue the solution to the question 3, the other part, in the next video, because it's from set proofs, and this one is the intersection index sets. So there are different topics together. So let's have the next tutorial for the final question in this past paper.